Hello everyone, welcome to the next lecture in our physiology video lecture series. This lecture is titled Body Fluids and Kidneys. In this particular lecture, we'll go briefly through the different kinds of body fluids and look in detail into the renal systems and the functioning of the kidneys. So let us start with the lecture. First off, let us look into our body fluids and different compartments present in our body fluid. This is a schematic that shows a simplified view of of different compartments in the body fluid itself. The total body fluid is distributed mainly between two compartments, the extracellular fluid and the intracellular fluid, which is, as the name is obvious, the intracellular fluid is the fluid that is present inside cells, and the extracellular fluid is the fluid that is present outside the cells. The extracellular fluid is further divided into interstitial fluid and blood plasma. So, if you remember the last lectures, interstitial fluid is the tissue fluid or the tissue gel that is present in the tissues just outside the capillaries. Just outside the capillaries, and the blood plasma is the acellular part of the blood, that is the part of the blood that is where there are no cells present. The intracellular fluid compartment is about 28 of the total 42 liters of body fluid, and this fluid consists of the fluid present inside 75 trillion cells that our body is composed of. So this is the intracellular fluid compartment, which is shown in the diagram. Next, we go into the extracellular fluid compartment. All the fluids outside the cells are collectively known as extracellular fluid. So all this part is the extracellular fluid. The two largest compartments of extracellular fluid include the interstitial fluid, which makes up more than 3/4 of the extracellular fluid. So we have interstitial. The extracellular fluid is further divided into, as I said, interstitial fluid about 11 liters, and blood plasma, which is about 3 liters. As I said, the interstitial fluid and blood plasma are divided from each other via the capillary membrane, so that they do not come to direct contact. And the cells are present in the interstitial fluid, which forms the extracellular matrix as well for the different tissues and cells. And both of them are divided via the individual cell membranes. The plasma, which makes up almost 1/4 of the extracellular fluid, or about 3 liters, and is the non-cellular part of the blood, which is shown right here. Plasma contains high concentration of proteins, and ionic compartments of both interstitial fluid and plasma are almost same. So the essential difference between interstitial fluid and plasma is the higher concentration of proteins in the plasma itself. And we also have the lymphatic circulation shown here, which obviously is the route via which heavier substances such as macromolecules and proteins and cell debris can move from the interstitial fluid into the blood plasma, as we have seen in the circulation videos, that heavy or larger proteins cannot move via the capillary membrane, and thus in order to move from the interstitial fluid to plasma, that is back into circulation, they have to take the route of lymphatics. And here we also have a diagrammatic representation of intake of fluid, that is via our food or via drinking water, and then the output or excretion of fluid via the kidneys, lungs, feces, sweat, and skin. Next, we have the constituents of intracellular and extracellular fluid. The different constituents are shown diagrammatically. So to start off, we see that the extracellular compartment has a large amount of sodium ions, and intercellular compartment has a huge amount of potassium ions. This is probably the topic that we have looked into again and again from the first lecture itself, that the extracellular fluid is abundant in sodium, while the intracellular fluid is abundant in potassium. The amount of calcium and magnesium is higher on the intercellular side and lower on the extracellular side. The anion chloride, the chloride anion also follows a similar trend as sodium ion and has a higher concentration on the extracellular side and a lower concentration on the intracellular side. Most of the organic anions such as amino acids or nucleic acids as well as phosphate groups are present in huge disparity in the intracellular fluid, which is obvious because the cell, mostly it is the cell itself which is the manufacturing unit of these organic anions. Next, we have higher concentration of carbonate, bicarbonate ion in the extracellular fluid, and a very large concentration of proteins in the intracellular fluid, which is obvious as intracellular fluid is the place where again proteins are manufactured. The plasma proteins which are shown here, so these are the plasma proteins which are shown right here, because as we have just discussed, if the extracellular fluid has two compartments, the interstitial fluid and the plasma, and as the plasma is the fluid higher concentration of protein, so this protein concentration that we can see in the extracellular fluid is obviously carried mostly by the plasma. The plasma proteins shown here have a net negative charge and therefore tend to bind to cations such as sodium and potassium, thus holding extra amounts of these cations in the plasma along with the plasma proteins. So if we look at the plasma itself, then the plasma is rich in cationic ions such as sodium and potassium, whereas the interstitial fluid, on the contrary, will tend to have slightly higher amounts of negatively charged ions because they do not have these negatively charged proteins that will hold on to cationic ions such as sodium and potassium. Thus, plasma has higher amount of positively charged ions and interstitial fluid has higher amounts of negatively charged ions. So conversely, negatively charged ions tend to have a slightly higher concentration in interstitial fluid because compared to plasma, the negative charges of the plasma proteins repel the negatively charged anions, and as anions can mostly flow freely through the capillary membrane, they move into the interstitial fluid. The extracellular fluid, including the plasma and the interstitial fluid, contains large amounts of sodium and chloride ions, reasonably large amounts of bicarbonate ions, but only small quantities of potassium, calcium, magnesium, phosphate, and organic acids or organic acid ions. The composition of extracellular fluid is carefully regulated by various mechanisms, but this is especially regulated via the kidneys. So next we move on to the kidneys themselves. First we look into the various functions of the kidneys. The first function of the kidneys are the excretion of metabolic waste products and foreign chemicals. This is probably the most important function of the kidneys itself. The kidneys are the primary means for eliminating waste products of metabolism that are no longer needed by the body. These products, including urea, which is generated from the metabolism of amino acids, it is an end product of the metabolism of amino acids. Creatinine, which is derived from muscle creatine, and uric acid, which is the end product of metabolism of nucleic acid, and other foreign substances. The next function of kidneys is regulation of water and electrolyte balance. For maintenance of homeostasis, excretion of water and electrolytes must be precisely matched to the intake of these of the liquid and electrolytes. The plot shown here describes the response of kidneys to a sudden tenfold increase in sodium intake. So if suddenly our intake of sodium increases tenfold, from a low level of 30 milliequivalents per day to a high level of 300 milliequivalents per day, we are able to see that the sodium excretion also increases by a huge rate. So the dotted line shows us the excretion of sodium, and the bold line shows us the intake. As the intake of sodium increases 10 times, we see that the sodium excretion also follows suit after a little lag and matches the excretion in order to maintain constant amounts of sodium ions in the blood plasma as well as the extracellular fluid. And then when we decrease the sodium concentration back to the original levels, after a while the excretion rate also drops down to the original level in order to still again maintain a constant sodium concentration. This is how the kidneys maintain and regulate water and electrolyte balance. Next, we look into regulation of arterial pressure. The kidneys play a dominant role in the long-term regulation of arterial pressure by excreting variable amounts of sodium and water. The kidneys also contribute to short-term arterial regulation by secreting vasoactive substances or factors. In the previous plot itself, we also see that when the excretion of sodium ions increased by a lot, the extracellular fluid volume also increased by some bit. This is mainly because both the intake and the excretion both increased, but kidneys were still able to maintain a constant amount of extracellular fluid volume. That is, they also regulated the water that was present in our body, even though they were excreting sodium at a much higher. So we now move on to regulation of acid-base balance by the kidneys. The kidneys contribute to acid-base regulation along with lungs and body fluid buffers by excreting acids and by regulating the body fluid buffer stores. Next, the secretion and metabolism and excretion of hormones and vitamin D3 production are also maintained by the kidneys. The kidneys produce the active form of vitamin D, which is 1,25 dihydroxy vitamin D3 or calcitrol. Calcitrol is essential for normal calcium deposition in bone and calcium reabsorption by gastrointestinal system. The kidneys also play a role in regulation of erythrocyte production. The kidneys secrete erythropoietin, which stimulates the production of red blood cells. As we have seen in our blood cells video, kidneys erythropoietin is very important for the generation of red blood cells. And one of the important stimulus of erythropoietin secretion by the kidneys is hypoxia, or the condition in which there is low concentration of oxygen present in our extracellular fluid. This part is also very discussed in detail in the blood cell video that we have already seen before, and I urge you to look into it if you are interested in erythrocyte production or erythrocyte production and secretion of erythropoietin by the kidneys. Next, the kidneys also have a role to play in gluconeogenesis. The kidneys synthesize glucose from amino acids and other precursors during prolonged fasting and thus control the overall amount of glucose present in the extracellular fluid as well. Kidneys also have this role to play in maintenance of glucose amount in the blood as they reabsorb large amounts of glucose from the urine that is being generated, and thus can play a role in maintenance of higher amounts of glucose or regulation of amounts of glucose present in the extracellular fluid. Next, we move on to physiological anatomy of the kidneys. Here we have a diagram showing the different parts of the kidneys. The two kidneys lie on the posterior wall of the abdomen outside the peritoneal cavity and weigh around 150 grams. The medial side of each kidney contains an indented region, which is this indented region, which is shown right here, called the hilum, through which pass the renal artery and the renal vein, lymphatics, nerve supply, and the ureter. So this is the entry of the renal artery, and this is the ureter that is shown right here. The two major regions of the kidney are the outer cortex and the inner region, which is referred to as the medulla. So this is the outer cortex, and after the dotted line we have the medulla. The medulla is divided into multiple cone-shaped masses of tissue called the renal pyramids. These red triangular structures are known as the renal pyramids. The base of each pyramid originates at the border between the cortex and the medulla and terminates in the papilla, which projects into the space of renal pelvis. Renal pelvis is the further this region which is inside the medulla, and this renal pelvis which will later converts to form the ureter. The outer border of the pelvis is divided into open-ended pouches called major calyces that extend downward and divided into minor calyces. The minor calyces collect urine from the tubules of each of the papilla, and then the whole structure forms into the ureter, through which the urine is carried to the bladder itself, which is shown right here. So this was the physiological anatomy of the kidneys. Next, we look into micturition. Micturition is the process by which the urinary bladder empties when it becomes filled. This involves two main steps. First, the bladder fills progressively until the tension in its walls rises above a threshold level. This elicits the second step, which is the nervous reflex called micturition reflex that empties the bladder, or if this fails, at least causes a conscious desire to urinate. Next, we look into the innervation of the bladder and how exactly the nervous system controls the micturition reflex. The urinary bladder is a smooth muscle chamber composed of two main parts: the body, which is the major part of the bladder in which urine collects, that is this balloon-like portion, and the neck, which is the funnel-shaped extension of the body connecting to the urethra, which is the portion right here. The principal nerve supply of the bladder is by the way of the pelvic nerves, which connect with the spinal cord through the sacral plexus, mainly connected with the cord segments S2 and S3, which is shown right here. Coursing through the pelvic nerves are both sensory nerve fibers and motor nerve fibers. The sensory fibers detect the degree of stretch in the bladder wall, and the motor nerves transmit in the pelvic nerves via parasympathetic fibers. Next, we move on to the structure of the nephron, which is the functional unit of the kidney. So here we have a diagrammatic representation of the nephron itself. Each kidney in the human contains about 1 million nephrons, each capable of forming urine. The glomerulus, which is this smaller red structure that is shown right here, contains a network of branching and anatomizing glomerular capillaries that, compared to other capillaries, have high hydrostatic pressure. So this glomerulus essentially is connected to a efferent artery and the efferent artery, which bring blood to the glomerulus where it is filtered. So essentially, this is the place where the filtration function of the kidney is done. The glomerular capillaries are covered by epithelial cells, and the total glomerulus is encased in the Bowman's capsule, which is this surrounding layer right here. Fluid filtered from the glomerular capillaries flow into the Bowman's capsule and then into the proximal tubule, which is this structure right here, which goes up to this position, which lies in the cortex of the kidney. So as I said, the kidney is divided into two halves, cortex and medulla. The nephron is present half and half in each. So the proximal tubule is present in the cortex itself. From the proximal tubule, the fluid flows into the loop of Henle, which is this loop right here, which dips into the renal medulla. So the lower portions of the nephron are present in the medulla itself, which starts with the loop of Henle. Each loop consists of a descending and an ascending arm and an ascending arm. The walls of the descending limb and lower end of the ascending limb are called thin segment of the loop of Henle. So these segments are thinner than the other parts of the loop of Henle and known as thin segment of loop of Henle. After the ascending limb of the loop has reached partway back to the cortex, up to this point, after this it becomes the thick segment of the ascending limb, where the thickness of the loop of Henle increases. At the end of the thick limb is a short segment, which is actually a plaque in the wall known as the Macular Densa. And as if we look closely, we will be able to see that the Macular Densa flows very closely to the back. Macular Densa is situated very close to the glomerulus. So if we have to know why this happens, the answer is very simple. The thing is that Macular Densa provides a feedback loop to the glomerulus that we will see in later slides, and this position in which the Macular Densa is situated in helps in the glomerulus detecting what the composition of the liquid of the filtered liquid exactly is, and after that the filtration rate and other parameters can be changed, and thus the Macular Densa plays a feedback role in the whole filtration system. Beyond the Macular Densa, fluid enters into the distal tubule, which is right here, which, like the proximal tubule, lies in the renal cortex. So we have come back into the renal cortex itself. This is followed by the connecting tubule and the cortical connecting tubule, which lead to the cortical connecting duct, which is present right here. The initial 8 to 10 cortical collecting duct join to form a single larger collecting duct that runs downward into the medulla, becoming the medullary collecting tubule and the medullary collecting duct. The collecting ducts merge progressively, larger ducts that eventually empty into the renal pelvis through the tips of the renal papillae. And these papillae then join progressively in order to carry the urine directly to the ureter through the ureter into the bladder. Now we'll look closely into the process of urine formation. The rate at which different substances are excreted in the urine represents the sum of three renal processes. The first is the glomerular filtration. The rate of filtration at which the different substances present in blood, which comes via the afferent arterial, are filtered through the glomerulus, followed by the reabsorption of substances from the renal tubules into the blood. So after filtration, as the fluid travels down the proximal tubule and other parts of the renal tract, they can be reabsorbed back into the peritubular capillaries that are running alongside them. And thus this changes the composition of the fluid that was filtered. Next, there may be secretion of substances from the blood into the renal tubules as well. In addition to reabsorption into the peritubular capillaries, the capillary may secrete further substances into the different parts of the renal tubules, and thus again affect the composition of the urine that is being formed. Thus, we can say that urinary excretion is actually a summation of three different forces. First is filtration, second is reabsorption, and third is secretion. Reabsorption obviously has a different opposite sign to others because reabsorption absorbs substances back into the blood and reduces their concentration in the urine. Urine formation begins when a large amount of fluid that is virtually free of protein is filtered from the glomerular capillaries into the Bowman's capsule. Virtually free of proteins is important, as we have seen again and again. The capillary walls are the capillary intercellular clefts are not large enough to allow proteins to pass through them, and thus the liquid that is filtered does not have large amounts of does have very low concentration of proteins in them. So they are virtually absent of protein. Most substances of protein apply in the plasma, except proteins, are freely filtered so that their concentration in the glomerular filtrate, which is the filtrate present here, in the Bowman's capsule is almost the same as in the plasma. As filtered fluid leaves the Bowman's capsule and passes through tubules, it is modified by reabsorption of water and specific solutes back into the blood, or by secretion of other substances from the peritubular capillaries into the tubules. Next, we will look into 4 substances A, B, C, and D, which have different nature, which are different in nature and undergo the processes of filtration, absorption, and secretion in various manners. And using these substances, we can understand a bit how the kidney filters different substances in our blood. The substance shown in panel A is freely filtered by the glomerular capillaries, but is neither reabsorbed nor secreted. Therefore, its excretion rate is equal to the rate at which it was filtered. So the substance A flows directly, the amount of filtered substances flow directly into the urine and is not affected by reabsorption or secretion. Certain waste products in the body, such as creatinine, are handled by the kidneys in this panel. In panel B, the substance is freely filtered but is also partly reabsorbed from the tubules back into the blood. So the substance first is filtered into the glomerular filtrate and is then reabsorbed. Some of it is reabsorbed back into the blood. Therefore, the rate of urinary excretion is less than the rate of filtration at the glomerular capillaries. In this case, the excretion rate is calculated as the filtration rate minus the reabsorption. This is typical for many of the electrolytes of the body. In panel C, the substance is freely filtered at the glomerular capillaries, but is not excreted into the urine, because all of the filtered substance is reabsorbed back from the tubules back into the blood. So a huge amount of the substance is, almost all of the substance C that was filtered into the glomerular filtrate is reabsorbed back into the blood via the peritubular capillaries. This pattern occurs for some of the nutritional substances in the blood, such as amino acids and glucose. The substance in panel D is freely filtered at the glomerular capillaries and is not reabsorbed, but additional quantities of this substance are secreted from the peritubular capillary blood into the renal tubules. So the most of the substance D was filtered into the glomerular filtrate, and whatever was left and was being carried into blood was secreted back into the renal tubules by the peritubular capillaries, so that the blood that is going out via the efferent arterioles, efferent artery or arterioles are virtually absent of the substance D, because all of it has been first filtered and then secreted back into the renal tubules themselves. This pattern often occurs in case of organic acids and bases, permitting them to be rapidly cleared from the blood and excreted in large amounts in the urine. So these are the 4 scenarios which can occur via occur while glomerular filtration by the kidneys, and the 4 substances A, B, C, and D are real life substances, are examples of normal substances that are handled by the kidneys on an everyday basis. Next, we look closely at the glomerular capillary membrane itself. The glomerular capillary membrane is similar to that of other capillaries, except that it has three instead of the usual two major layers. The layers of the glomerular capillary membrane include the endothelium of the capillary and the basement membrane, both of which are present in normal capillary membranes as well. But there is an additional third layer, which is a layer of epithelial cells known as podocytes, surrounding the outer surface of the capillary basement membrane. The high filtration rate across the glomerular capillary membrane is due to partly its special characteristics. The capillary endothelium is perforated by thousands of small holes called fenestrae. Fenestrations are relatively large endothelial cells. Fenestrations are relatively large, and endothelial cells are richly endowed with fixed negative charges that hinder the passage of plasma proteins. Surrounding the endothelium is the basement membrane, which consists of a meshwork of collagen and proteoglycan fibrillary that have large spaces through which large amounts of water and small solutes can filter through. The final part of the glomerular membrane is a layer of epithelial cells that line the outer surface of the glomerulus, that is the podocytes. These cells are not continuous but have long foot-like processes that encircle the outer surface of the capillaries. The foot processes separated by gaps called slit pores, through which glomerular filtrate moves. The epithelial cells, which also have negative charges, provide additional restriction to the filtration of plasma proteins. So these are the three layers of the glomerular capillary membrane, which have very important roles to play in the glomerular filtration. Next, we look into the filterability of solutes based on molecular sizes and charge. First, we have a table which shows us filterability of substances based on the molecular weight. As we can see, the low molecular substances such as sodium, water, and glucose, even which are have very low molecular weights, with water having a molecular weight of 80, have a filterability of 1, or 100% or have a filterability of 1. The substances which have higher molecular weight, little by little, have lower filterability, with myoglobin, which has a molecular weight of 17,000, has a filterability of 75% compared to that of water. And albumin, which is a blood plasma protein, has a molecular weight of 69,000 and a filterability of only 0.5% compared to water. Thus, the heavier or the larger mass of the particular substance that is being filtered, the filterability lowers dramatically. Next, we see that filterability also has an effect, is also affected by the charge of the substance being filtered. When dextran, which is a polymer of glucose, was filtered through the kidneys, but filtered through the kidneys, we have the following graph. The dextran that was filtered was different on only the basis of the charge that it was carrying. So we have polycationic dextran, which is positive, neutral dextran, which has no charge at all, and polyanionic dextran, which is negatively charged. As we can see in this graph, polycationic or positively charged dextran has the highest relative filterability, while polyanionic dextran has the lowest relative filterability. Thus, we can conclude that the filtration by the glomerulus is also dependent on the charge, and positively charged substances are more readily filtered out from the system. Next, we move on to the glomerular filtration itself. Urine formation begins with filtration of fluid through the glomerular capillaries into the Bowman's capsule. The glomerular capillaries are relatively impermeable to proteins, so that the filtered fluid, which is called the glomerular filtrate, is essentially protein-free and devoid of cellular elements including red blood cells or RBCs. The concentrations of other constituents of the glomerular filtrate, including most salts and organic molecules, are similar in concentration to that of plasma. The glomerular filtration rate is mainly determined by the balance of hydrostatic and colloid osmotic forces acting across the capillary membrane and the capillary filtration coefficient Kf, which is the product of the permeability and filtering surface of the capillaries. So Kf is essentially a constant that cannot be manipulated. It means absolutely dependent on the structure of the capillaries and the glomerulus. The glomerular capillaries have a much higher rate of filtration than most other capillaries because of high glomerular hydrostatic pressure in a large scale. In the average adult human, the GFR is about 125 milliliters per minute or 180 liters per day. In this particular diagram, we have a blown up picture of the glomerulus itself, showing us the podocytes and the fenestrations, that are present in the endothelial membrane. And these are the three layers of the glomerular capillaries, which include the endothelium layer, which has the fenestrations, the basement membrane, and these are the podocytes that are present right here. Next, we look into the determinants of glomerular filtration rate. We when expressed mathematically, glomerular filtration rate or GFR can be expressed as the product of Kf and net filtration pressure. The net filtration pressure represents the sum of hydrostatic and colloid osmotic forces that either favor or oppose filtration across the glomerular capillaries. These forces include first the hydrostatic pressure inside the glomerular capillaries, which is the glomerular hydrostatic pressure described by Pg, which promotes filtration. Hydrostatic pressure in Bowman's capsule, Pb, outside the capillaries, which opposes filtration. Colloid osmotic pressure of the glomerular capillary plasma proteins, Pg, which opposes filtration. And colloid osmotic pressure of proteins in the Bowman's capsule, Pb, which promotes filtration. But as we have seen under normal circumstances, the Bowman's capsule has very low protein concentration in its glomerular filtrate, and thus as this concentration is close to zero, the colloid osmotic pressure of proteins in the Bowman's capsule is also close to zero, and thus the fourth parameter can be effectively neglected. Thus, we have a final working equation which gives us the net filtration pressure, which is equal to glomerular hydrostatic pressure minus the Bowman's capsule pressure and minus the glomerular osmotic pressure. The glomerular hydrostatic pressure comes to about 16 millimeters of mercury. The Bowman's capsule pressure is about 18 millimeters of mercury, and the glomerular osmotic pressure is around 32 millimeters of mercury, to give the net filtration pressure of 10 millimeters mercury. Next, we move on to factors affecting GFR. Increased glomerular capillary filtration coefficient increases GFR. The Kf is a measure of product of hydraulic conductivity and surface area of glomerular capillaries. And as we have seen in the previous diagram, previous slide, in this equation, if Kf increases, then GFR will obviously increase. But as Kf is constant and depends absolutely on the structure of the glomerular capillaries and the glomerulus itself, the changing of Kf is not a primary mechanism for change in GFR. Next, we have increased Bowman's capsule hydrostatic pressure, which will decrease the GFR. Increasing hydrostatic pressure in Bowman's capsule will reduce GFR because it is a negative, it contributes negatively towards the GFR itself. However, changes in Bowman's capsule pressure normally do not serve as primary means for regulating the GFR. In certain pathological states, however, which are associated with obstruction of the urinary tract, such as kidney stones, can increase the Bowman's capsule pressure itself. So Bowman's capsule hydrostatic pressure can increase, but this is often correlated with the pathological states and is not the normal mechanism by which GFR is controlled. Next, we move on to the third parameter that can affect the glomerular filtration rate, which is the glomerular capillary colloid osmotic pressure. About 1/5 of the fluid in the capillaries filter into the Bowman's capsule, thereby concentrating the glomerular plasma proteins that are not filtered. So consider this, that a certain concentration of proteins was flowing into the glomerulus with a volume of say 100 liters, when they or 100 milliliters, but 1/5 of the fluid, that is around 20 milliliters, flows into the Bowman's capsule. So when the exiting fluid in the glomerular capillaries now has the same amount of proteins, but only in 80 milliliters of plasma volume. What this means is that as the volume decreases, but the amount of proteins stay the same, therefore concentration of the proteins increases. Thus, the glomerular capillary colloid osmotic pressure in the glomerular capillaries increases. Increasing the arterial plasma colloid osmotic pressure raises the glomerular capillary colloid osmotic pressure as well, which in turn decreases the GFR. So, glomerular capillary colloid osmotic pressure can also be affected by the arterial plasma colloid osmotic pressure. Thus, two factors influence the glomerular capillary colloid osmotic pressure, which include the arterial plasma colloid osmotic pressure and the fraction of the plasma that was filtered by the glomerular capillaries, or the filtration fraction. The point to note that when the filtration fraction increases or greater volume of fluid flows into the Bowman's capsule, then the glomerular colloid osmotic pressure increases. Whereas in case the filtration fraction decreases or less volume is filtered into the Bowman's capsule, then the filtration fraction decreases with respect to the normal glomerular osmotic pressure. So when the filtration fraction increases, glomerular colloid osmotic pressure increases. When the filtration fraction decreases, the glomerular colloid osmotic pressure decreases. Next, we move on to the glomerular capillary hydrostatic pressure and how it affects GFR. So, glomerular capillary hydrostatic pressure has a direct relation with GFR, and thus increase in capillary hydrostatic pressure or increases the GFR. Changes in the glomerular hydrostatic pressure serve as the primary means for physiologic regulation of GFR. Increase in glomerular hydrostatic pressure raises the GFR, whereas decrease of glomerular hydrostatic pressure reduces GFR. Glomerular hydrostatic pressure is determined by three variables, which include the arterial pressure, the afferent arteriolar resistance, and the efferent arteriolar resistance. Afferent arterial is the one that is carrying blood into the glomerulus, and efferent arterial is the one that is carrying blood out of the glomerulus. Now let us look into how these affect the glomerular hydrostatic pressure and in turn the GFR. The efferent arteriolar constriction has a biphasic effect on GFR. At moderate levels of constriction, there is a slight increase in GFR. But with severe constriction, there is a decrease in GFR. So biphasic, like two types of effects that can be shown. Constriction of efferent arterioles increases the resistance to outflow from the glomerular capillaries. Efferent arteriolar constriction raises the glomerular hydrostatic pressure, and as long as this increase in efferent resistance does not reduce renal blood flow too much, GFR increases slightly. So we have to consider that when the efferent arteriole constricts, the resistance to outflow increases, and thus the pressure or the glomerular hydrostatic pressure increases. And as increase in glomerular hydrostatic pressure has a positive impact on GFR increases. But since efferent arteriolar constriction also reduces renal blood flow, the filtration fraction and glomerular colloid osmotic pressure also increase as the efferent arteriole resistance increases. Therefore, if constriction of efferent arteriole is severe, the rise in colloid osmotic pressure exceeds the increase in glomerular capillary hydrostatic pressure, which is caused by the efferent arteriolar constriction. And thus, this is the reason because behind why the efferent arteriole constriction has a biphasic effect on GFR. And this is shown as a diagram via diagram right here. As we see, when the efferent arteriole resistance increases in the x-axis, the GFR first increases but then starts decreasing. This is in direct correlation with the amount of renal blood flow. Efferent arteriolar resistance, as expected, decreases the renal blood flow, but after a point, when the renal blood flow decreases too much, then this also affects GFR, and which decreases GFR further. Thus, when this occurs, the net force of filtration actually decreases, causing a reduction in GFR. So this was the effect of efferent arteriolar constriction. Now we move on to afferent arteriolar constriction, which is the arteriole which is bringing blood to the glomerulus. Increased resistance in the afferent arterioles reduces glomerular hydrostatic pressure and decreases GFR. Conversely, dilation of the afferent arterioles increases both glomerular hydrostatic pressure and GFR. So afferent arteriolar constriction has a straightforward effect on GFR and glomerular hydrostatic pressure, which is if the afferent arterioles constrict, then the GFR will decrease rapidly, as well as the renal blood flow will also decrease rapidly. But on the other hand, if the afferent arterioles dilate, then both of them will start increasing. Now we will look into, in close detail, into renal blood flow. Renal blood flow is determined by the pressure gradient across the renal vasculature, which is the difference between renal artery and renal vein hydrostatic pressure, divided by the total renal vascular resistance. That is renal artery pressure minus renal vein pressure by the total renal vascular resistance. We've already encountered this formula, which is known as Ohm's law, in the circulation videos, in which blood flow was determined as del P by R, or pressure divided by resistance to the flow of blood. Renal artery pressure is about equal to systemic arterial pressure, and renal vein pressure averages about 3 to 4 millimeters mercury in most conditions. Resistance of these vessels is controlled by sympathetic nervous system, where various hormones and local internal renal control mechanisms. Although changes in arterial pressure have some influence on renal blood flow, the kidneys have effective mechanisms for maintaining renal blood flow and GFR relatively constant over an arterial pressure range of between 80 to 170 millimeters of mercury, which is known as autoregulation. This capacity for autoregulation occurs through mechanisms that are completely intrinsic to the kidneys and unique to the kidneys, and we'll look into autoregulation specifically in later slides. Next, we move on to physiological regulation of glomerular filtration and renal blood flow. The determinants of GFR that are most variable and subject to physiologic control include glomerular hydrostatic pressure and glomerular capillary colloid osmotic pressure. These variables in turn are influenced by the sympathetic nervous system, hormones, and autopoids, which are vasoactive substances that are released in the kidneys and act locally, and other feedback controls that are intrinsic to the kidneys. The sympathetic nervous system activation decreases GFR. All blood vessels of the kidneys, including afferent and efferent arterioles, are richly innervated by the sympathetic nervous system. Strong activation of renal sympathetic nerves can constrict the renal arterioles and decrease renal blood flow and GFR. In healthy resting person, sympathetic tone appears to have little influence on renal blood flow. But in case of severe acute disturbances like brain ischemia or severe hemorrhage, the renal sympathetic nerves can reduce GFR. Now we look into the hormonal and autopoid control of the renal circulation. The hormones norepinephrine, epinephrine, and endothelin constrict renal blood vessels and can decrease the GFR. Hormones that constrict afferent and efferent arterioles, causing reductions in the GFR and renal blood flow, include norepinephrine and epinephrine, which are released from the adrenal medulla. Another vasoconstrictor, endothelin, is a peptide that can be released by damage to vascular endothelial cells of the kidneys as well as by other tissues. Endothelin also acts as a powerful vasoconstrictor which contributes to hemostasis as well. Angiotensin II constricts the efferent arterioles and is another hormone. A powerful renal vasoconstrictor, angiotensin II can be considered a circulating hormone as well as a locally produced autopoid because it is formed in the kidneys as well as in the systemic circulation. Angiotensin II preferentially constricts efferent arterioles, glomerular, which in turn increases the glomerular hydrostatic pressure while reducing the renal blood flow, as we have just seen. The angiotensin II prevents decrease in GFR and glomerular hydrostatic pressure when arterial pressure or blood volume drops. In this particular table that is shown right here, we can show the relations between the different hormones or autopoids and GFR. As we have just discussed, norepinephrine, epinephrine, and endothelin decrease GFR, whereas angiotensin II can increase or decrease GFR as it affects the efferent arterioles, and as we have just seen, efferent arterioles have a biphasic reaction on GFR and thus they can increase or decrease, but essentially we can say that angiotensin II prevents the decrease of efferent arterioles. Next we move on to endothelial derived nitric oxide, which is released by the renal vasculature and which is released by the kidneys and can decrease the renal vascular resistance and increase GFR. A basal level of nitric oxide production appears to be important for the maintenance of vasodilation in the kidneys. This allows kidneys to excrete normal amounts of sodium and water, and therefore administration of drugs that inhibit this normal formation of nitric oxide increases renal vascular resistance, which in turn decreases GFR and urinary sodium excretion. Prostaglandins and bradykinin also tend to increase GFR. Hormones and autopoids that cause vasodilation and increase renal blood flow and GFR include prostaglandins, which is PGE2 and PGI2, and bradykinin. They may dampen the renal vasoconstrictor effects of the sympathetic nerves or angiotensin II, especially their effects to constrict the afferent arterioles. By opposing vasoconstriction of afferent arterioles, The prostaglandins may help prevent excessive reductions in GFR and renal blood flow. Next, we move on to an important topic in GFR regulation, which is autoregulation of GFR and renal blood flow. Autoregulation is a feedback mechanism intrinsic to the kidneys, which normally keep the renal blood flow and GFR relatively constant despite marked changes in arterial blood pressure. This relative consistency of GFR and renal blood flow is independent to the systemic influences and is referred to as autoregulation. GFR normally remains autoregulated, that is relatively constant, despite considerable changes in arterial pressure due to a person's usual activities. For instance, a decrease in arterial pressure to as low as 75 millimeters of mercury or as high as 160 millimeters of mercury causes minute changes in GFR. In general, renal blood flow is autoregulated in parallel with GFR, but GFR is the parameter that is more efficiently autoregulated under certain conditions. Next, we move on to the point that why is GFR autoregulated or why is GFR autoregulation necessary? Normally, GFR is about 180 liters per day and tubular reabsorption is 178.5 liters per day, leaving 1.5 liters per day of fluid to be excreted in the urine. In the absence of autoregulation, a relatively small increase in blood pressure, say from 100 to 125 millimeters of mercury, with cause a similar 25% increase in GFR from 180 to 225 liters per day. If tubular reabsorption remained constant at 178.5 liters per day, this would increase urine flow to 46.5 liters per day, which is essentially calculated as the difference between GFR and tubular reabsorption, and thus there is a total increase of more than 30-fold of urine production. As the total plasma volume is only 3 liters, a 46.5 liter per day urine excretion is practically impossible and will quickly deplete the blood volume. But in reality, such a change in arterial pressure exerts much less of an effect on urine volume for two major reasons. Renal autoregulation prevents large changes in GFR that would otherwise occur, and there are additional adaptive mechanisms in renal tubules that allow them to increase reabsorption rate when GFR increases, which is known as glomerular tubular balance. Thus, this scenario that we have just discussed does not occur in daily life, but renal autoregulation firstly maintains the GFR at a constant rate, so that at say 25% or similar increase in arterial pressure does not affect GFR, and in case it and further glomerular tubular balance further increases the reabsorption, which is this particular value 168.5 liters per day, and thus which prevents excess urine formation and excretion of an excretion of fluid from the body. So we move on to the next point, which is looking into detail in autoregulation and how it occurs. First, we will look into the role of tubulo-glomerular feedback in autoregulation. This is a blown up picture of the glomerulus, and as we had discussed when we were looking into the nephron structure, we have the efferent artery and the afferent artery, as well as the macular densa that we said was related to the feedback mechanism which controls the amount of fluid that is reabsorbed and the GFR as well. To perform the function of autoregulation, the kidneys have a feedback mechanism that links changes in sodium chloride concentration at macular densa with the control of renal arteriolar resistance. The tubulo-glomerular feedback mechanism has two components that act together to control GFR. The first being the afferent arteriolar feedback mechanism and the efferent arteriolar feedback mechanism. These feedback mechanisms depend on the juxtaglomerular complex, which consists of macular densa cells in the initial portion of the distal tubule and juxtaglomerular cells in the walls of the afferent and efferent arterioles. The macular densa cells contain Golgi apparatus, which is directed towards the arterioles, suggesting that these cells may be secreting a substance towards the arterioles. Next, we look into the mechanism of autoregulation of GFR. Experimental studies have suggested that decreased GFR slows the flow rate in the loop of Henle, because obviously, if fluid is not being filtered into the glomerulus, the flow rate in the through the loop of Henle, which is connected to the proximal tubule, will also decrease, causing increased reabsorption of sodium and chloride ions in the ascending loop of Henle. This reduces the concentration of sodium chloride at the macular densa cells. This decrease in sodium chloride concentration initiates signal from the macula densa that has two effects. First, it decreases the resistance to blood flow in the afferent arterioles, which raises glomerular hydrostatic pressure and helps return GFR towards normal. It also increases renin release from juxtaglomerular cells of the afferent and efferent arterioles, which are major storage sites for renin. Renin released from these cells then function as an enzyme to increase the formation of angiotensin 1, which is subsequently converted to angiotensin 2. As we know, angiotensin 2 constricts the efferent arterioles and therefore increases the glomerular hydrostatic pressure, returning GFR towards normal. Thus, this whole thing is shown as a flow chart in this diagram right here. When arterial pressure decreases, this causes a subsequent decrease in glomerular hydrostatic pressure. This decreases GFR. As GFR decreases, the glomerular filtrate stays in the loop of Henle and other parts of the renal tubules for longer, which causes higher amounts of sodium and chloride to be absorbed while the filtrate travels through the renal tubules. Finally, when the fluid through the tubules arrives at the macula densa, the NaCl concentration is lower than normal. This allows this lower concentration of NaCl detected by macula densa cells, which causes two different functions. First, it directly causes a decrease in afferent arterial resistance, which increases glomerular hydrostatic pressure. And secondly, it increases the production of renin, which in turn increases the production of angiotensin 1, which is converted to angiotensin 2. Thus, increased in amount of angiotensin 2 is there, which then increases efferent arteriolar resistance. Efferent arteriolar resistance, as we have seen, has a positive effect on glomerular hydrostatic pressure, and thus it increases glomerular hydrostatic pressure, which in turn increases GFR, and thus the GFR is auto-regulated via the macula densa cells. This was the mechanism of how auto-regulation occurs. This was all we had for today. These are the references for the slides, which are the chapter 25 and 26 of textbook of medical physiology by Arthur C. Guyton, the 11th edition. I thank you for listening to this video.